So I'd like to thank the organizers and also students who made great effort for this conference. And I'm going to talk about symplectic capacities from Hamiltonian cell collections, and this is joined with Professor Cho. So first I will remind what the symplectic capacity is, and then talk about the relation with cell collections. So, let me start with the definition of symplectic manifold. So it is a manifold with a two form, which is closed and non-degenerate. So non-degeneracy means that we have a vector in tangent bundle, and using this map, this is an isomorphism between tangent and cotangent bundles. So if we think about smooth functions on M, then we can differentiate and we can think about the composition of this map. And let's denote the image by XH. So this one is called the Hamiltonian vector field. And one simple but important observation is that this vector field preserves symplectic form omega. So what this means is that any smooth function gives us automorphism of the manifold. So symplectic geometry is very flexible. But on the other hand, it has also rigidity properties, and this is well shown in the following theorem. So this is called Gromov non-squeezing theorem. And so consider a 20-dimensional ball of radius r, and we want to embed this thing into a product of disk and Euclidean space. And the volume on the left-hand side is finite, and the volume of the right-hand side is infinite. So we can always embed this, preserving the volume. But if we want to embed this thing, preserving the symplectic form, then we should have that the small r is not greater than the capital R. And so from this theorem, we have the following definition of Gromov-Witten. So Gromov-Witten, so we will denote it by WG, and this is defined to be the supremum of pi r squared, and here R is the ball embedded in M. And by the definition, we have the following properties. So first one is, if M1 embeds into M2, then so they have the same dimension. then we see that width is not greater than the ambient one. And second property is that if we scale symplectic manifold by a constant lambda, then so the width of this thing is just the multiplication.
Vertices and edges be an invariant.
And third property is that width of the ball of
these three graphs
and the ball of the width of the product,
okay,
is equal to pi. And now let's forget about this Gromov width and think about some quantity satisfying these three conditions. So here we note that if there is some quantity satisfying let's denote these three properties as star, then if something satisfies this property, then we see that this Gromov non-squeezing theorem is automatically proved. So non-squeezing. So actually we can now, because of that, we consider this star as an axiom of symplectic capacity. Axiom for symplectic. So, if we find another symplectic capacity, then we will. We have another proof of this non-squeezing theorem. So let me introduce one more symplectic capacity. This one is called Hofer-Sender capacity. And this is denoted by CHC. So this one is defined for general symplectic manifold, but for simplicity, let's assume that manifold is closed. Then suppose following two things. The first one is
for the right hand side is an
open set U and V, such that restricted to those open sets, it takes minimum and maximum. And second condition is that this Hamiltonian vector field of function H has no non-constant orbit of period less than 1. And then this invariant is defined to be the maximum, the difference of the maximum and the minimum. So if you want to make this thing bigger, sorry, this is so if you want to make this thing bigger just by scaling this function, then the period would be getting less and less. So, I mean, we cannot make this thing arbitrarily large, and this one turns out to be a symplectic invariant.
This is the definition of the capacity.
Yes, so these three are the definition.
Not the whole capacity, that's the definition.
Yeah, so these are definition. Capacity. So which
I'm saying you are that H max minus H min is the definition of CH.
yes, right. Yeah. Yeah, so this one is definition. So
And second, can you one more time say what's H max, what's H min?
so H is a function on M, and we assume that just H is M is closed, and this one is a maximum and minimum of that function. Sorry, which one is it? No, it doesn't depend on H. So, sorry. So, this one, I'm sorry. So, yeah, this one should be supremum. Sorry. Yeah, thank you. So now let me talk about Hamiltonian actions. So we have a circle action on M. Then this will give us a fundamental vector field on M. Yes, we have a vector field on M, and we say the action is Hamiltonian if this is Hamiltonian. Equivalently, this means that there is a real valued function H such that dH is equal to omega x bar. So let me give you one simple example. So suppose circle X on a sitting inside Euclidean space, and the action is by the diagonal. So then the moment map is given by summation of pi times ci squared. And we can observe the following two things. First one is this ball is the inverse image of the moment map of this interval. And second thing is the period here, the period of Hamiltonian vector field is okay, sorry. Yeah, so the first one says that the moment map is related to the embedding of balls, and second one says that it is also related to the Hofer-Zehnder capacity. So let me state our main theorem. So suppose M omega is a closed symplectic manifold with Hamiltonian circle action. So we have a moment map H. So we have a, and because M is closed, we have a, the image is a closed interval. So it's H. Yeah, and there should be finitely many critical points. I'll just denote. Sorry, this should be max. And here S max is the second critical values. And now assume that the inverse image of maximum is a point. And second, the action is semi-free. So equivalently, this one is the weight is
This kind of
0 or plus minus 1. They're the same condition, and then our result is that Gromov width is given by the difference between maximum and the second maximum one, and the Hofer's and the capacity is given by the difference between maximum and minimum. So let me first give an example that this theorem applies. So examples are complex Grassmannians, and some I'm sorry, I forgot one important condition. So this should be Fano. So what I mean by Fano is that so every symplectic manifold has a compatible almost complex structure, and Fano means every holomorphic sphere should have positive area. And yes, this one is Fano condition.
Sorry, with your notation, Gromov-Witten is H max minus H.
S max. So sorry. So S max is a second critical value.
H by minus H.
Yes, we can. Yeah, right. Yeah, right.
Then I switch the maximum and the minimum. So
Yes.
does it imply that the difference between the maximum and the second maximum is the same as the difference between the? I mean, assuming that also the minimum has a sigma.
Yeah. So if minimum is a point, then the difference should be the same.
Okay. So how to get
Sorry. WG. I'm
Is it obvious that this is the same?
Maybe not. I'm not sure. So
See, when you can modify your Hamiltonian, changing the distance between minimum, second minimum or maximum, second maximum, and
So how-
width doesn't change because it's independent from the Hamiltonian.
yeah, right.
This is bizarre.
여기 let's assume.
Why? I mean, how can you deform this H? Because I mean H is given by the action, and it's I mean, in some sense I think it's some reason. Yes, yes, but the action should satisfy those two conditions. And for semi-free action is, this one is rather, I mean.
But it's generic. I mean, you can add very small.
No.
If you little bit change it may not be a vector action.
So some toric Fano manifold. And also
your condition was that H restricted to some open set.
Yes. Yes. Sorry. Yeah.
The button inverse image of maximum I think is a point.
Yes. Sorry?
Isn't that open set contains H inverse? Is contains H inverse?
I'm sorry, I couldn't understand.
So H is attains H maximum in some open set.
Yes.
But you are saying that H inverse of maximum is just 1 point.
Sorry, so in this case, H is on any smooth function. So, I mean, so this is taking supremum among all H. But now, this H is given by the action, and so actually, so from this moment, so if we slightly change this H, then we can make it to have minimum on an open set. Okay. And some product. Not product of those, I mean, those examples. So for this Torifano manifold, let me just give some examples. So in dimension 2, there are only five types of Fano manifold. So let me just draw the image of the moment map. So first one is a product of spheres, and second one is P2, and those are blow-ups. And this two. And so for first 4 cases, there is such an action, but this one, there is no such action. So we couldn't prove, we couldn't compute the Gromov width of general toric Fano manifolds, and as dimension goes high, there are more examples that doesn't have this section. So we need another method. And so for the remaining time, let me just briefly talk about how we prove this theorem. So actually, it is a combination of other results. So we have WG and CHC, and we find lower bound and upper bound, and then we compare them and check that they are the same. Yes?
Why the last one? Which condition?
I mean, so the sub-circle action should satisfy those two.
Both
But
are not.
both. I mean, one of them is not satisfied if we choose in any direction. So, for example, if we choose in this direction, then this one has isotropy weight 2. So, yeah, no. So, and lower bound is, there is a result by Karlsson and Tolman. So as we saw in this example, locally the neighborhood of the maximum should look like a ball, but their result is that we can extend that ball until we meet the second critical values. So actually, by their result, we can find the lower bound. And for Hofer-Zehnder capacity, actually it's direct. Just we modify a little, and then we can show that that one is a minimum. And for upper bound, so first one is due to Gromov, and second one is due to Lu. And for this one, we need to consider some Gromov-Witten invariants. So I don't know. So roughly speaking, the Gromov-Witten invariant is a count of curves passing through some given cycles. And yeah, so let me just write down their result. So Gromov's result is that if
in a 8-dimensional case, in this,
so first one should be point and so intuitively, this means that we are counting curves in, so here A is a second homology class, and alpha i's are, just any cycles in them. So, and this one is a number of, in this case it's just spheres. Sphere passing through alpha I, and class is A. So this means that, so first one is a point, so this means that given a point, there is a holomorphic sphere passing through that point. And if that's the case, the Gromov-Witten is bounded above by the area of that curve. And Lu's theorem is that it's almost the same, but we need.
I guess it's just these two cases. Okay, you get this kind of class.
Yeah, so now the problem is to find some non-vanishing Gromov-Witten invariant, and for that we use Seidel representation. Yeah, so this one appeared in the previous talk as S, but now I have 1 minute, so yeah, so the main idea is to use result by McDuff and Tolman. So this representation is hard to compute in general, but if the loop in Hamiltonian group is given by a circle action, then there is a way to compute it. I mean, not completely, but we can get some information on it, and then so using their ideas, we can prove those two things. Thank you very much.